Hello everybody and welcome back to another video. In today's video we will be deriving the equation for the escape velocity of an object. Now let's start off by looking at the energy of an object with a velocity straight upwards of v relative to a point surface of that planet, which has a radius of r naught. So this velocity v gives the object the kinetic energy, which is the total energy since it only has kinetic energy in this case, of 1/2 mv squared. So our energy right here is equal to 1/2 mv squared. Now let's assume that we let time progress and this object gets further and further and further away and slower until it is infinitely far away and has a velocity of 0. As infinitely far away, there would be no force acting on the object, and a velocity of 0 would mean that it's just stationary, infinitely far away. So, since there are no net forces on the system, we know that the change in energy is equal to 0. So, let's say we have that point infinitely far away be our E2, where there's only gravitational potential energy. Then we know E1 equals E2, which means our potential gravitational energy is equal to 1/2 mv squared. This is v, not r. Now let's call this mass of the object launched. Now, let's look right here, where last video we learned that the area under this graph right here is equal to the change in energy as you move an object from an initial radius to a radius further away. Now, the energy, that is assuming there's an external force. What this actually means is the change in potential energy. So let's assume that this is our initial radius of r naught, and let's move r1 all the way infinitely far away, so that we are looking at the area infinitely under this curve, also known as you're looking at the energy is equal to the integral from r naught to infinity of the force of gravity with respect to the radius. So our energy is equal to this equation right here, where G is Newton's gravitational constant. This is the mass of the object, this is the mass of the planet, and this is r naught, the distance away. That's not r naught, that's just r. So we will integrate this from r naught to infinity. Now this technically is an indefinite integral. I'm not going to be doing the whole limit definition as I want this video to be quick. However, it does work out, and I know that because I've dealt with many problems like this in the past. Now, all this stuff on top is a constant with respect to the radius, so we could pull that out of the integral. So we get our energy is equal to a gravitational constant times the mass of the object times the mass of the planet times the integral from r naught to infinity of r to the negative 2 dr. Now, using our power rule for integration, we get our second energy is equal to negative 1 over r from the bounds r naught to infinity, which is equal to this constant times negative 1 over an infinitely growing piece, so this is all equal to 0, minus negative 1 over r naught, the negatives cancel, so this is times 1 over r naught. So we get that our energy at this point is equal to GMO MP over r naught. Now, let's use this as this right here. So we know that 1/2 mv squared, so the kinetic energy at the beginning, is equal to GMO MP, this is MO by the way, over R naught, which is our potential energy at the end. So this is a conservation of energy equation. We have the mass of the object on both sides, so we will divide by MO on both sides, which cancels out here, here, and here. So we have 1/2 v squared is equal to the mass of the planet times Newton's gravitational constant over r naught. So when we multiply both sides by 2 now, we get that v squared is equal to 2gmp over r naught. And then we can take the square root of both sides and we get our velocity is equal to radical 2gmp over r naught. This is our final equation right here, where g is Newton's gravitational constant, mp is the mass of the planet, and r naught is the distance away you started from the planet. So this is our work from today. We derived an equation. This will give you the gravitational potential energy, this right here, and then this will just give you the escape velocity. Let me know if you found this video helpful and useful, and if you understood what I was talking about today. Leave any questions, comments, concerns in the comments down below. And please like and subscribe if you want to see more content like this, and thank you for watching.